I'd like to welcome everybody to this afternoon's event, this doctoral thesis defense. And most especially, I'd like to welcome the doctoral candidate, Kristian Sommer Thygesen, and the two official opponents, Professor Lucia Reining from École Polytechnique in Paris, in Palaiseau, in France, and Professor Nicolas Mazzani, École Polytechnique Fédérale de Lausanne, in Switzerland. Also, welcome to Professor Henning Friis Poulsen, the Department of Physics at DTU. He is the chairman of the assessment committee. My name is Rasmus Larsen. I'm the provost and a chief academic officer at this university, and I'll be the chairman of the proceedings this afternoon. So these proceedings will be as follows. So after my small introduction here, the doctoral candidate, Kristian Sommer Thygesen, will take the podium and present his thesis that's entitled Electronic Excitations in Two-Dimensional Materials and van der Waals Heterostructures, in a lecture of approximately 30 minutes length. Thereafter, we'll have a small break. And when we come back from the break, the two official opponents will enter into discussion, ask questions, expect answers from the candidate. After the two official opponents have exhausted their lists of questions or exhausted the knowledge of the candidate, whichever comes first, there will be the opportunity for questions ex auditorio. Now, if there are unofficial opponents in the auditorium, please contact me in the break after the lecture. Now, before we begin, I should also add there is one more important item. So when all discussions have ended in here, and the formal part of the defense is over, then the Technical University of Denmark will host a small reception outside in the lobby, immediately outside the auditorium, and I hope all of you will join us out there. Now, before we begin, I'd like to say that in these years there is a very dominating agenda in that we see how digitalization is changing every industry, product, service, and almost every human endeavor. This is really dramatic, how information and communication technology, big data and Internet of Things bring new opportunities to all engineering areas. But I think it's very important to remember that this is not the only thing that is happening. There are other basic disciplines that bring disruption too. Biology is one. Biology and bioengineering will bring many new opportunities into the engineering disciplines. We'll see bio-inspired solutions, confluence of electronics and biology, and so on. Now, a third trend is in material science. So material science has brought and will continue to bring dramatic changes in all engineering fields. New materials with amazing and sometimes unexpected properties emerge and gives us new possibilities for engineering products in all the engineering areas. And this, I think, is something that we will learn more about today, about materials on the smallest scale, about molecular electronics representing new and exciting low-cost nanoscale alternatives to the conventional semiconductor devices that we have in all our IT equipment, potentially making it possible to reduce all these things in size. I think there are great perspectives there. Now with this, I would like to end my small introduction and invite Kristian Sommer Thygesen to the podium to present his work. Værsgo.
Thank you very much, Rasmus. I just need the pointer here. So, welcome to all of you. I'm very happy to see so many people have showed up here today. As Rasmus already said, the title of my thesis is Electronic Excitations in Two-Dimensional Materials and van der Waals Heterostructures. And I'm sure there are a number of you who don't really know what these words mean. So I will start by explaining in simple terms what a two-dimensional material is. So a two-dimensional material is atoms that are bonded together by chemical bonds in a two-dimensional fashion, like shown up here. This is the case of graphene, where carbon atoms are bonded together. The thickness of such a material is then just a single atom, or maybe a few atoms. So this is less than 1 nanometer. This corresponds roughly to 100,000 times thinner than a human hair. And these materials can be on the order of square centimeters large when they are produced. So this means we're talking about extremely thin materials. And because they are so thin, these materials, they can have a number of very special properties that are very different from the properties we know of materials that are thicker and more conventional. So to illustrate that, I'm using graphene, which is by far the most well-known two-dimensional material and also the first that was discovered. Graphene is a fantastic material. It's the best electrical conductor that we know. It has a room temperature mobility, which is 100 times larger than that of silicon, which is the basic material that is used in electronics today. It's the strongest material known. It's roughly 100 times stronger than steel. It's an exceptional heat conductor, one of the best known heat conductors. It's almost transparent. So it has good electronic conductivity and is transparent at the same time, which seems to be in conflict with our normal perception of a metal. It's lightweight and it's highly flexible. It can be stretched by 20% before it breaks. And then in addition to all these fantastic practical properties, it also hosts electrons. So electrons in this material, they behave very different from electrons in all other known materials. And that has led to a number of very exciting fundamental discoveries, physics discoveries over the past decade, and some of them are listed here. Okay, so the field of two-dimensional materials has developed extremely rapidly over the past decade since graphene was discovered back in 2004. And let me try to give a very brief review of this history, focusing on some of the milestone discoveries that have been made. So the starting point is the isolation of graphene in 2004. Then in the years between 2004 and 2010, all these remarkable properties that I just mentioned of graphene were discovered. And that led ultimately to the Nobel Prize award to Andrei Geim and Konstantin Novoselov in 2010. And around the same time, research in other types of two-dimensional materials took off. And one of the most interesting classes that were discovered at the time were the transition metal dichalcogenides, of which molybdenum disulfide is the most well-known example. And in contrast to graphene, which is a so-called semi-metal, it doesn't have a gap between the occupied and unoccupied electronic states. These materials were semiconductors, and that means we can begin to use them for electronics and optics. And already 1 year after their discovery, the first field effect transistor, based on a single layer of MOS2, was produced. The year after, in 2012, it was discovered that one can excite charge carriers in these semiconductors selectively in different valleys of the semiconductor using circularly polarized light. And that adds another degree of freedom to the charge carriers in the material. So in addition to charge and spin, now the valley index can also be controlled. And that led to a new field called valleytronics that took off at that time. In 2013, Andrei Geim and co-workers produced the first so-called van der Waals heterostructures, which are heterostructures produced by combining different types of two-dimensional materials, forming a vertical stack, as shown here, and that opened up completely new perspectives, because now we can begin to engineer materials also taking advantage of the third dimension. In 2014, another by now very famous two-dimensional material called phosphorine was discovered. And in 2015, different types of light-emitting diodes based on both lateral and vertically layered heterostructure devices were developed and fabricated. Last year, it was discovered that some of these two-dimensional materials can host quantum light emitters. That is, they can emit single photons, and that holds great perspectives for different disciplines in quantum technologies like quantum communications. This year, the first ferromagnet, two-dimensional ferromagnet, was discovered in the form of chromium iodide 3. And then, with all these materials discovered, one can ask, okay, how many are there? And I think a first good answer to that came also this year by different groups, in particular Nicola Massari, who's one of the opponents here today, who looked at all the known crystals, all the crystals that have been synthesized today, and looked at how many of those are actually layered and could be exfoliated to single layers. And the answer is more than 1,000. So there is a huge number of two-dimensional materials out there that we can potentially take off and study and recombine again by using the concept of heterostructure layering. So I should say at this point, perhaps mainly as a curiosity, that the idea of designing materials by stacking two-dimensional materials is not new. The American physicist Richard Feynman, who was a very visionary person, already back in 1959, gave a very famous talk called Plenty of Room at the Bottom, where he said, imagine what we could do with layered structures if we just had the right layers. What would the properties of such materials be if we could arrange the atoms or the layers in exactly the way we wanted? So I think these days, or these years, we are experiencing this vision of Feynman is about to come true. We can really arrange these two-dimensional layers in the way we want them. Here's an example, just a couple of weeks old, published in Nature, where wafer-scale semiconductor films, so these are films that are square centimeters in area, were produced, and you can see here they consist of single layers of different two-dimensional materials. Such semiconductor heterostructures really form the basis of all digital electronics today. And typically these films are tens of nanometers thick, and there are various problems. They are very hard to produce. You can only stack materials in this way if the lattice constant of the materials match. But these types of materials, lattice mismatch is not a problem. And the reason is that the materials themselves are chemically inert, and therefore they don't form covalent bonds in the third dimension. You can see these. This is a TEM picture, a transmission electron microscope picture. You can see black lines in between. And that's because the bonding between the layers is weak. This is called van der Waals bonding, and thus the name van der Waals heterostructures. And this means we can put any types of two-dimensional layers together. Here's a tri-layer of 3 different semiconductors. So this is an illustrative but very simple calculation one can try to do. So imagine we have 10 different two-dimensional materials at our disposal. In reality, I think we know about 30 today that have been isolated. How many possible combinations can we make? How many three-dimensional materials can we make if we stack these layers to form a heterostructure with 10 layers? That number is 10 to the 10th. So that's an astronomical number. And as I said today, we know that there are probably not just 10, but more like 1,000 different two-dimensional materials out there. So that means this number is huge. And this also shows that we really need to understand, and we need methods that can predict in a relatively quick way the properties of these types of materials if experimentalists should have any chance of designing and producing materials with tailored properties. So after this general introduction, I come to my own contributions, which is described in the thesis. So what I've considered in the thesis are electronic excitations in these two-dimensional materials. And in particular, I have looked at, when I say I, you should always understand me and all my fantastic co-workers that have contributed. I'll come back to that in the end of the talk. But we have considered 3 different types of excitations in these materials called quasiparticles, excitons, and plasmons. A quasiparticle, that's an electron or a hole in a solid together with its screening cloud. Okay, and the energy of the quasiparticle forms what is known as the band structure of the material. An exciton, that's a photoexcited, or that's an electron-hole pair, photoexcited electron-hole pair, which is due to the attractive interaction between the negatively charged electron and positively charged hole, is bound together and forms a bound state with an energy that lies inside the band gap of a semiconductor. A plasmon is a collective quantized oscillation of the electron system in a metal. In combination, these three types of excitations determine the electronic and optical properties of a material. So therefore, understanding them and developing computational methods that allow us to predict and rationalize the properties is extremely important. They can be measured by various types of experimental probes, STM, optical absorption, electron energy loss, etc. Before we can begin to understand and calculate electronic excitations in any material, we have to understand the concept of screening. We have to understand how two electrons, or an electron and a hole, interact with each other inside the material. If they're in free space, this is Coulomb's law. This is just something that scales with 1 over the distance. But here is a two-dimensional material, and there is a positive and negatively charged a particle in here. And what you can see is that the field lines, most of them actually go through vacuum. And that means that in contrast to three-dimensional materials, where all the field lines are inside the material, then the screening will be very weak. So that's the first thing to remember. Screening is very weak in two-dimensional material. The other thing is, as you can imagine, when these particles are close together, a relatively large fraction of the field lines are still inside the material. But when the particles are very far away, almost all the field lines are in the vacuum outside. And that leads to a very non-trivial dependence of the screened interaction, which does not follow what we know from 3 dimensions. And mathematically, this means, if we look at what is called the dielectric function as a function of wave vector q, that for a 2-dimensional material, we get the green line. This is hexagonal boron nitride, a single layer. That's the green line. That's the static dielectric constant, and the dashed line is bulk hexagonal boron nitride. We can see for large Q vectors here, where Q is larger than the inverse thickness of the material, the screening properties are similar to in 3 dimensions. Okay? This corresponds roughly to the situation in real space where the particles are close to each other. But when the particles are far away, that means we have wave vectors in reciprocal space that have wavelength that is longer than the thickness of the material, then there is a clear deviation and the dielectric function becomes linear in Q rather than constant, as we know from 3-dimensional systems. So this is the mathematical consequence of these peculiar screening effects in 2 dimensions. So there is a number of consequences of this particular form of the screening in 2 dimensions, and I've listed some of them here. And I say unique because all these effects here are very different in 2-dimensional materials compared to the well-known phenomena from 3 dimensions. And they can all be traced back to the peculiar type of screening in 2-dimensional materials. Now, 2-dimensional materials are usually not alone in the universe. They are typically put on a substrate or they are embedded in a van der Waals heterostructure. And since the Coulomb interaction is long range, it means that the effective interaction between the two particles now will be very sensitive to the environment of the 2-dimensional material. So that's of course a complication if we want to do calculations or if we want to interpret experiments, we have to take the environment into account. But it also has a very attractive opportunity because it means we can begin to tune the effective interaction between particles in this material and thus the electronic structure of the material by controlling the external dielectric environment. So we have a way of now engineering properties and electronic excitations in the 2-dimensional materials. So how can we calculate dielectric functions or screening properties of van der Waals heterostructures? We've developed what is called the QE, or what we call the Quantum-Electrostatic Heterostructure model, or QEH in short, which calculates the dielectric properties of a heterostructure, shown here, by taking each of the 2-dimensional entities here and then computing what we call the dielectric building block for each of them. So this is for an isolated 2D material. We calculate a low-dimensional representation of its full dielectric function using full-fledged quantum mechanical calculations. And then we couple the different layers using the dielectric building blocks. We couple them together only by the Coulomb interaction between the layers. So that's a classical coupling mechanism, and that provides us enables us to calculate the full dielectric function of this material. So with that, we can now calculate the effective interaction between an electron located up here and another electron located down here. So we have full control over the dielectric properties of the heterostructure using this method. So does it work? Yes. Here's an example where we computed the so-called plasmons in a heterostructure composed of two graphene layers here with insulating hexagonal boron nitride in between. And what we find is two different types of plasmons. One is a symmetric and an antisymmetric combination of the sheet plasmons in the graphene layers because they hybridize and interact with each other. And what I'm showing down here is the plasmon dispersion of the two modes calculated using the QEH model. That's the full lines, and the symbols is what we get from a full quantum calculation of the entire heterostructure. And you can see the agreement here is, I would say, almost too good. We can do these full quantum calculations up to 3 layers of HBN, but with the QEH model, we can calculate that for any number of HBN layers in between. So we can go to much larger structures. So the method works. Okay, so now I'd like to turn to band structures and how screening affects band structures in two-dimensional materials. Here is a band structure, and the band structure gives the binding energy of electrons and holes in the material. They can be measured experimentally by shooting photons into the material and ejecting electrons, and then by measuring the kinetic energy of this electron, we can infer what is the energy of the hole that it has left behind. We can do the same thing for the unoccupied states here by inverse photoemission. Theoretically, we can calculate these energies by solving what is known as the Quasiparticle equation. The Quasiparticle equation has a simple part, which is the kinetic energy and the external potential set up by the crystal. And then it has a complicated part, which is called the exchange correlation self-energy. And that self-energy physically describes the interaction of electron with its screening cloud. So the electron polarizes the material, and then the electron interacts with that polarization cloud. And that's described by the self-energy. That self-energy in the widely used GW approximation, which is the approximation that has been used throughout the thesis, takes this form mathematically. What I want to show you here is that the screened interaction between electrons enters explicitly in this expression. So this shows that by manipulating the screened interaction, we should be able to manipulate the self-energy and thus the band structure of the material. Okay, here I'm just showing you what we can do with computational material science today. Here we calculated the band edges, so the top of the valence band and the bottom of the conduction band for 50 different two-dimensional semiconductors. And there's a lot of information in this plot that I don't have time to go into detail with today. But one thing we were interested in here is finding good candidates for doing water splitting and hydrogen evolution, which is in a very important chemical reaction for the production of chemical fuels. But what I want to show now is how good the agreement is with experiments when we do these calculations. So I should say that there are two types of calculations up here. The red bars is this GW method that we are using, and the blue is a more standard single particle approximation called LDA. Now, if we take the GW result and we compare the conduction band minimum and valence band maximum to experiments, the gap between the two is calculated to 2.5, and that's in very good agreement with experiments. So on the band gap, we're in very good shape. We can really predict those very accurately. If we look at the absolute position of the conduction band here and compare to measured electron affinities, the agreement is not so good. And the reason for that is a technical one, but we are missing what is called the vertex corrections in the self-energy. This is probably mainly for the opponents. And the vertex corrections are really important in predicting the absolute energy of these levels. And if anyone else should be interested in this, I should say that we have a PhD defense on Tuesday by Per Schmidt, who's working in the group, who's looked at this problem and developed vertex corrections that can actually fix these problems to a large extent. This is also work together with Thomas Olsen. Okay, so coming back to the effect of screening. The calculation I showed you before were all for isolated two-dimensional layers. What happens if these two-dimensional layers are in contact with other two-dimensional layers or a substrate? So we look at this system here, which is hexagonal boron nitride, which is an insulator with a large band gap, and graphene. Here's the band structure, calculated again both with GW and LDA. This is where we have the band gap of hexagonal boron nitride, or HBN, between the red bars. What is the energy of an electron in this material? Well, it has the energy that it has in hexagonal boron nitride. But now there is a graphene layer on top. That negatively charged electron will induce a positively charged image charge in the graphene layer, and there will be a positive interaction between the two. That's a correlation effect that we have to take into account. And in the simplest classical description, we could use an image charge model to model this, and then we would expect a 1 over distance dependence of the band gap in hexagonal boron nitride, dependent on the distance to the graphene. And that's exactly what we find. So this is a 1 over distance fit to the GW calculations of the band gap in hexagonal boron nitride. You can see this is the gap in freestanding HBN. So we can actually reduce the gap quite significantly by putting it onto a layer of graphene. The problem with this from a practical point of view is that it's very difficult to perform calculations of these heterostructures, GW calculations of these heterostructures. This system here is roughly the largest you can do today. So to solve that problem, we've developed another method where we compute the energy of an electronic state of a two-dimensional layer embedded in a heterostructure. So this would be layer I, a state Nk. We write that as the energy of the electron in an isolated two-dimensional layer, which we can easily calculate. And then we add corrections due to hybridization between the layers. That's easy, we can do that with DFT. And there is a correction due to this screening effect, which is much more complicated. But we can calculate that using the QEH model, because we can calculate the change in the electronic screening between the electron and the other electrons in the system. So we can do that very cheaply, and that leads to the G delta W method that we've developed, which allows us now to calculate quasiparticle band structures of heterostructures with hundreds of layers. So I think that really opens up new perspectives in the field. Here you can see the calculated band gap of different semiconductors when they are embedded in 2 layers of graphene. And the point here is just that we can really tune the band gap quite significantly here by modulating the dielectric environment, by embedding the semiconductor in different types of two-dimensional materials. Okay, so now let me switch gears and talk about excitons. As I've already said, an exciton is an electron-hole pair in a semiconductor, which are forming a bound state in the band gap due to the Coulomb interaction between the electron and the hole. Okay, so the binding energy of the exciton is the distance between the exciton energy and then the band gap. That's an important parameter called the exciton binding energy. Another important parameter is the size of this exciton, so the average distance between the electron and the hole in the semiconductor. That's called the exciton radius. In a many-body quantum mechanical language, this excitonic wave function is a superposition, it's a highly correlated state, a superposition of electron-hole pairs created over the entire Brillouin zone. We can take the expansion coefficients here, and then one can show that the Fourier transform of these expansion coefficients, which are defined in reciprocal space, satisfy this simplified Schrödinger equation, which is called the Mott-Wannier model. So this is a drastic simplification, and if the screening is simple, so if it's just 1 over r times epsilon, as it is in 3-dimensional crystals, where we have a dielectric constant, then this is just a screened hydrogen atom in 3 dimensions. Okay. The point is this doesn't work in 2 dimensions, and let me show you why. Here are some measurements. These are measurements of the 5 lowest lying excitons, the 5 lowest energies of the Rydberg series in tungsten diselenide that have been measured. And here's a fit to a hydrogen atom. And you see that fit doesn't work very well. So what they did in this paper to explain this was they used the standard expression for the energies of a hydrogen atom, but then they used epsilons here, dielectric constants, that were state dependent. And by doing that, they could actually fit the experiments very well. Of course, it's not very satisfactory to fit these values to experiments, so we asked ourselves, can we calculate those ab initio, so without any fitting parameters? So the starting point is this hydrogen model now in 2 dimensions rather than 3 dimensions, and we have this screening constant down here. So what to use for that? The problem is that depends strongly on Q. right? So it goes to 1 here. So for Q going to 0, there is no screening at all in a two-dimensional material. So we can't just use a dielectric constant. That's the whole problem. So what we did, this was work together with Thomas Olsen, what we did there was instead to average the dielectric constant here over the inverse radius of the exciton. Okay, that's a technicality, but that's roughly the screening wavelengths that are important for the exciton. If we do that, and we combine that with the analytical expressions we have for a two-dimensional hydrogen atom, then we can actually end up with analytical expressions for the effective dielectric constant, now state-dependent, but calculated analytically, the energy and the radius of the excitons. Does it work? Yes, it works very well. Here's a comparison again. What do we get with the analytical results compared to more accurate calculations? If these dots had fallen on this diagonal here, there would be perfect agreement. So there is a bit of scatter, but it's actually quite good overall. A very interesting thing here is if we look at our analytical expression, then the mass actually drops out to a good approximation. So the mass of the electron and the hole, the effective mass, doesn't enter the expression for the binding energy. This is again very different. In 3 dimensions, the energy is proportional to the mass. So that's a novel two-dimensional effect. Another thing is that the model explains is the observed linear scaling between the exciton binding energy and the band gap of the material, because the polarizability alpha here, or the dielectric constant of the material, goes roughly as 1 over the band gap of the material. Okay, so that's also well explained by this expression. So coming back to the initial example here, these were the fitted values for the dielectric constant, and what we get with our model calculated ab initio is a very good agreement, and therefore the exciton energies we calculate are also in very good agreement with the experiments. I should add here that it's very essential to take substrate screening into account. So if we do these calculations for an isolated layer of tungsten diselenide, we get the green energies over here. So the experiments are the red. If we use the QEH model to include the screening from the substrate, what we get is the blue here, again in very good agreement with the experiments. Okay, so the last example, if I have 5 minutes, concerned plasmons, and in particular the different nature of plasmons and excitons. And again, there are some things when we compare excitons and plasmons which are very different in 2 dimensions compared to 3 dimensions. So this was a collaboration with Superstem at Daresbury, which is a scanning transmission electron microscopy facility, which are specialized in making very high resolution, both spatial and energy-wise. So it's TEMs that are well suited for studying electronic excitations. So what we looked at were different flakes of MOS2. So here is a sample where you can see from this TEM image different terraces here corresponding to different thicknesses of the MOS2. So the thinnest are around 3 layers, and the thicker one here are close to bulk MOS2. So this is a TEM image, and over here is shown EEL spectra. So this means you take the electron beam, you place it at a particular point over the sample, and then you measure the energy loss at that particular point, and you get a spectrum out as a function of energy. You can now take that energy spectrum and you can integrate it, and here it's integrated over the area where the excitons are sitting in the spectrum, and then you can produce a spatial map of that energy loss spectrum, and you can see it agrees very well with the TEM image. So the excitons are sensitive to the thickness of the material, and that's something we studied here, but that's not the point I'm going to make today. What I want to say today is the following. So if we calculate the EEL spectrum of this material here in the Q going to 0 limit, so in the long wavelength limit, which is what is relevant in optics, where you have photons. Photons don't carry any momentum really, so you can only probe the small q regime. Then we get the black curve up here. So it's completely flat in this energy regime where there's a lot of spectrum in the experimental spectrum. Okay, so all these features here are positioned where we would expect the plasmons to be. And we can infer that from plasmon calculations of bulk MOS2. But they don't show in our spectrum. So at this point, we have to remember that a very localized electron beam is not a plane wave in the lateral dimension, right? It's localized. So it has all kinds of momenta in plane. So really to reproduce the EEL spectrum of a localized electron beam, we have to sum over all the Q values. And then we get the blue curve. And you can see now we get a very nice agreement. Well, we get a better agreement, for sure, with the experimental spectra. There is still a lot of room for improvement, but we get these features, and they are indeed due to the plasmons. The plasmons develop at finite Q, so they are completely absent for Q equal to 0. And that's very different from the three-dimensional case, where plasmons typically dominate the yield spectrum for Q equal to 0. There is another interesting thing here, because what I've just said is that for small Q values, that is slowly varying fields, they can only couple to the excitons, whereas rapidly varying field, they couple to plasmons. And that you can actually see if you look at the yield spectra here. This is the spatial yield spectrum integrated over the range of the excitons. And you can see this is where the border of the sample is. And in this regime, the electron beam is actually parked outside the sample, and still there is a lot of signal. That's because the electron beam has a slowly decaying tail. The small Q values of the electron exciting the excitons. If we look at the plasmons instead, which we can look at by integrating the yield spectrum over this peak up here, then we see a much sharper transition from the sample into the vacuum region. So that's because we can only excite plasmons by the low Q values, by the rapid variations of the electron beam. Okay, this is again very different from the three-dimensional case. And with that, I would like to summarize the talk. So I hope you have a feeling now, share my feeling that two-dimensional materials are really a fascinating playground for exploring and controlling electronic excitations and electronic and optical properties of the materials. We are close to realizing, I think, Feynman's visions from '59, namely stacking two-dimensional materials in order to produce designed materials with tailored properties, targeting different types of applications. And finally, I hope I convinced you that these types of calculations provide basic fundamental understanding of the physics of materials, and also that they can provide, and are really essential, for providing guidelines that could lead to the rational design of novel materials in the future. And that brings me to the most important slide of this talk, which is the thank you slide. There is a very large number of people who I owe a lot. Thomas Olsen has been involved in a lot of the work I've talked about. Carsten Jacobsen and Jakob Schütz are my colleagues, and they're always very inspiring and have very many good ideas. And then all these young and talented people here have contributed a lot to the work, and I wouldn't stand here without the work from all these people here. Everyone in C&G here, I've just listed the people that I have common publication with. Not least computing and administration. Ole and Jens Jørgen are always making a perfect infrastructure, handling that in the most professional way. Marianne is helping a lot in the section in general and with the work of this thesis in particular. And then a lot of exceptionally good external collaborators that I've worked together with in the past years here. And thank you to all of you for coming and listening.